Okay, we're on the optimization problems. There's problems, I think, were taken from the James Stewart's calculus textbook. Anyway, let's take a look at the first question. As I do these things, I want to point out there's a variety of ways of doing this. At Essex County College, we're not using calculators. However, I will post a video of me using a calculator to do these problems as well. Okay, so find the dimension of the rectangle with area, 1,000 square meters. So the first thing to do is just draw a picture of a rectangle. I'm going to say X and Y. And then I'm going to say that it has the area of it is 1,000. And that's square meters, by the way. That means X times Y is 1,000. What they say is perimeter is as small as possible. Well, the perimeter is going to equal to 2X plus 2Y. All right, so what I'm going to do is try to write a function with one unknown, one variable. I'm going to say perimeter is a function of X. So it's going to be 2X plus 2 times, well, what's Y equal? You're going to use this equation here, and Y would equal 1,000 divided by X. I'm going to rewrite a little bit. And what do you get there? You get 2X plus 2,000 X to the minus 1. All right, so before I go on, I want to talk about the values that X could take on if it's a rectangle problem. And the X has got to be greater than 0. That's one thing for sure. All right, so what I'm going to do over here is take the derivative now and look for critical points. Critical points will be greater than 0, though. What do you get here? 2. And then you get minus 2,000 X to the minus 2. Right? It's undefined at 0, but that's not a critical value because it's not in the domain of the problem. So I'm looking for when this thing takes on to 0 now. And that's going to occur when 2 is equal to 2,000 over X squared. Or when X squared is equal to 1,000. All right? When does that occur? Well, it occurs when X equals plus or minus the square root of 1,000. I'm going to simplify that. The square root of 1,000, well, it's going to be, there's 100 there, so that's 10 root 10. So plus or minus 10 root 10. But again, they're not the critical numbers. Critical numbers, I'll put it on the number line now. We're starting at 0. And there's only one critical number, and that's 10 root 10. And what are we analyzing here? The derivative. And let's see what happens. So you take a test point. A good test point to choose between 0 and 10 root 10 would be 1. You plug it into the derivative, and what would you get over there? You get a negative number, which means the perimeter function is decreasing. Now if you take a number, if you take a number after 10 root 10, I don't know, 100, let's say, and plug it in, again to the derivative, what are you going to get? You're going to get a positive number, which means the perimeter function is increasing at that point. What's the question? Find the dimensions of a rectangle whose area is 1,000 square meters, whose perimeter is the smallest possible. Well, I just found the smallest possible perimeter. Let's write it down now. What's that going to be? They want the dimensions, which is going to be X by Y. So it's going to be 10 root 10. What's the dimension of that? Meters by, well, it's really not that bad to do. If you have to, go back over here and do it. And what I mean by that is 1,000, and it's going to be 10 root 10 times what? That's the Y value. It's got to be 10 root 10. It's a square. Meters. All right? Let's go to the next question. Next question is: a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders, I think he means that borders a straight river. He needs no fencing along the river. So I'm going to put the straight river down like this, and I'm going to put my fencing up now. So it's going to be fencing like this. Again, it's rectangular. I'll use the same letters. I'll call this X, I'll call this Y, and I'll call that X. Again, the river doesn't need any fencing. And what do I know about this? I know there's 2X plus Y is equal to 2,400, and this is in feet. All right, so a farmer has 2,400 feet of fencing. He wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. what are the dimensions of the field that has the largest area? Well, the area of this field is going to be x times y. Whoops. The area is x times y. I want to write a function of one unknown, and that unknown I'm going to choose is x. I'm going to get over here. Let's take a look. You're going to get x. What's y going to be? 2400. Whoops, I did it again. I'll erase that. I said 2400, but I wrote something different down, didn't I? 2400 minus 2x, and that's what y is. Where's that coming from? Right over here. All right, so I'm looking at this thing, and before I proceed, I want to talk about what x could be. X has definitely got to be greater than 0. However, it's got to be less than something. And what's going to be less than? Well, half of the 2400 is a 1200. All right, let's take a look now and take a simplification of this, and this is area function of x, 2400x minus 2x squared. Take its derivative now. Its derivative will be 2400 minus 4x. All right. The critical numbers are going to be between 0 and 1200. And looking at that, that's going to be what? That's going to be 600. That's a critical number. That's when it takes on to 0. So then the question comes, what are you going to do over here? Let's say I did this right. 2400. Yeah, I did okay. So let's take a look. And I got to write down something now, and I'm going to write the number line down. It starts at 0. It ends at 1200. I just want to check it again, make sure I said this right. 2x plus y is 2400. X times y is the area. Area is a function of x. Is going to be x times y, and y is 2400 minus 2x. That's 2400x minus 2x squared. Took its derivative, 2400 minus 4x. It looks okay. X is 600. Put this over here. Take a test point below 600, and this is the derivative we're analyzing, by the way. And it's going to tell me about the function itself. So take a number below 600, like, I don't know, 1, plug it in, it's positive. That means you've got an increasing problem there, area problem. And then if you go above 600, but below 1200, like 1000, plug it in, you get a negative number. Again, we'll plug into derivative. What do I know? I now have the value that I want that's going to maximize the area. What's their question? What are the dimensions of the field? Well, let's write this down. The x is 600. So it's 600 feet by, got to be careful over here. So it's this thing over here. I got to figure out what the y is. Well, if x is 600, 2 times 600 is 1200. You take 1200 from both sides and you get 1200. So it's 600 feet by 1200 feet. That's the dimensions. Let's go to the next question. And again, they go through a series of questions, and they're pretty straightforward, by the way. I don't see anything too complicated at this point. Okay, it says the top and bottom margins of a poster are 6 centimeters, and the side margins are 4 centimeters. The area printed area is 384 centimeters cubed. So I'm going to try to draw a picture, sort of, I'm not going to say it's terribly accurate, but a picture of a poster. I'm going to put this over here. And the border at top is 6, and the sides is 4. So maybe something like this. So I'm not saying I'm doing a great job of drawing a picture. All right? So I know something about this. I know the printed area, this thing over here. I'm going to call it x by y. I know x times y is equal to 384. All right, now someone says, what's their question? It says, find the dimensions of the poster. Well, the dimensions of the poster are going to be this over here. All right, what's this going to be? Y plus, remember it's got a border in top and bottom at 6 each, so that's 12. And over here, these are the side borders. Well, it's going to be x plus something. The side borders are worth 4 each, so it's going to be 8. So the area over here of this poster is going to be y plus 12, and then x plus 8. Again, I want to write down as a problem with one unknown. I'm going to write in terms of x's, and what's y going to be? 384 over x plus 12, and then x plus 8. I'm going to keep going through this, multiply it out. I get 384. I'm distributive product multiplication. Then I get 8 times 384, x to the minus 1. I just distribute this term across the x plus 8. Now I'm going to do this. That's going to be 12x plus 12 times 8. I'm going to take the derivative now. Derivative 384 is 0. The derivative next term is going to be minus 8 times 384, x to the minus 2. Then it's going to be plus 12. And then you get the derivative of 12 times 8, which is 0. All right. Now before I go on forward, I do know that x has got to be greater than 0. All right. And what am I looking at? I'm looking for some critical numbers over here. And to do that, let's take a look at this. I'm looking for when this takes on a 0 now. It's undefined as 0, but I'm not worried about that. When does it take on 0? It takes on 0 when, let's see, 8 times 384 over x squared would equal 12. So I'm going to, maybe do some manipulation over here. I'm going to start to reduce it. And I like to go, one thing at a time. I'm going to divide by 4. That becomes 3. This becomes 2. And 3 goes into 384. Let's put this down. 3 into 384. 1, that's a 3. Drop the 8 down, that's 2. That gives me 6, and then I get 24. That gives me 8, so 128. All right? So this could be 128. 2 times 128 is 256. X will equal plus or minus 16. So I'm going to put my analysis down, and my analysis starts at 0. 16 is the only critical number in this particular problem, and we're doing the derivative. It's going to tell us about the area. Take a number below 16. A good number below 16, again, we're checking it over here, would be 1, and if you plug that in, you get a negative number, which means the area function is decreasing. If you take a number above 16, I don't know, like 20, plug it in, you're going to get a positive number. All right, what do I know about this over its smallest possible area? What do they want? The question is find the dimensions, and we know a couple different things now. What do I know? I know x is 16. And what's y going to be equal to? Well, that's not the answer, by the way. Y is going to be 16 into 384. I'll put that down for you. That goes in 2 times. That's 32. Then you get 64. 16 times what? 64 is 4. So the y is 24. All right? I do want to write the answer down, though. So what is the answer going to be? Well, I'm looking at my picture. It's going to be x plus 8, which is 24. This is centimeters. By, well, the y is 24, but I'm adding 12 to it, and that's going to be 36 centimeters. All right, let's go to the next question. I kind of jammed that thing in there, I realized that. And the next question, I guess we have to go to question 4 now, right? Let's put question 4 down. And question 4 is find the dimension of the rectangle, largest area that has a base on the x-axis and its other 2 vertices above the x-axis lying on the parabola. So I'm trying to visualize it right now. So I'm going to visualize parabola first, relatively simple. Parabola looks sort of like this over here. And then I know the parabola's got a point here. The point of this parabola would be x. I'm above the x-axis, by the way. And the y-coordinate would be 12 minus x squared. Okay, I'm going to try to visualize the rectangle now. It's above the x-axis. It's got a base along the x-axis. It looks sort of like this over here. So I do see a good deal of symmetry, right? And this is going to be the rectangle. And I need to find a rectangle of the largest area. So the area of the rectangle is going to be a function of x. And I want to emphasize to you it's going to be the base. Before I say anything, though, I'm going to point out x will be greater than 0 and x must be less than the root of 12. And why is that? The point over here is going to be root 12. All right? So I know what my x is between 0 and root 12. So what I'm going to do now is write down the area function. And the base of the rectangle is actually 2 times x. The height of it is 12 minus x squared. I'm going to simplify the area function. And that's going to be 24x minus 2x cubed. I'm going to differentiate this, which is 24 minus 6x squared. I want to get the critical numbers between 0 and root 12. I'm kind of looking at that. It doesn't look that bad, actually. It's 24 would equal 6x squared. And that would be 4 equals x squared. And x would equal to plus or minus 2. Right, I know minus is not a possibility, though. Put my analysis down between 0 and root 12. And I got the x to be 2. I'll put it over here somewhere. All right, so what I'm going to do now is, this is the derivative. Plug in a number. What number would I pick between 0 and 2? 1. That would be positive. That means the area function is increasing. Between 2 and root 12, I'd probably say 3. And if you plug that in, you're going to get a negative number. That means the area function is decreasing. So what do I know about this over here? I think I know the answer to the question. Find the dimensions of the rectangle. Well, the dimensions are going to be what? The base of it is going to be twice the x, which is 4, by, what's the height of it going to be? Well, I'm looking at it, and again, I'm looking at that point over there. The height is going to be 12 minus 2 squared, which is going to be 8. I don't see any units on this, so it's a 4 by 8. Let's go to the next question. The next question, again, you're reading it, you might say, oh, geez, what do I need to know about this? Well, I would say just kind of visualizing it, and it might be more than enough just to visualize to understand what the question is. But anyway, this one says a right circular cylinder is inscribed in a sphere. Well, I'm going to draw a circle. And the circle looks like this. Not the best looking circle, but it's a circle centered at the origin. And the equation of this circle is going to be x squared plus y squared is equal to, well, raised to 4 would be 16. All right? So that's a circle centered at the origin. And now I gotta kind of visualize. I know my pictures aren't great. I got to picture like a rectangle in here. And that rectangle, I'm going to say that I want to keep the x's. I'll write this over here. I want the x to be greater than 0. Right? And what's the maximum it could be is 4. All right, then what I'm going to do is over here talk about the point. Right, the point here, again, this is the point, is going to be x, comma, the square root of 16 minus x squared. So I'm going to try to visualize the cylinder now. Looks like this over here. And again, I'm looking at this to visualize it. This would just be the x dimension over here. What's the height of this thing? Well, it's twice the y coordinate. What's the y coordinate going to be? 2 times the root of 16 minus x squared. All right, what's the volume of this thing over here? It's a function of x. It's going to be this area of the cross-section here, which is going to be pi r squared. Well, the r is x squared, times the height of it, which is 2, the square root of 16 minus x squared. I'm going to keep moving forward. I'm going to simplify it a little tiny bit. This is going to be 2 pi x squared times 16 minus x squared to the half power. I'm going to use I'm going to take the derivative of this thing over here, product rule certainly. So what do you get? 4 pi x times 16 minus x squared to the 1/2 power. Then it's going to be plus 2 pi x squared times the derivative of that root function, which is going to be 1/2. Then you're going to get 16 minus x squared to the minus 1/2 times the derivative of the inside, which is actually minus 2x. I'm going to factor that. And I'm looking at that, and it looks pretty difficult, but I think I can handle it. I'm going to say 2 pi x. We'll talk about this in a moment, by the way. And then I'm going to say 16 minus x squared to the minus 1/2 times, and 1/2 is what we're doing here. We're just doing one term at a time. I want to do this one first. And I factor out 2 pi x, so I'm left off with 2. Put that down for you. And I'm left off with 16 minus x squared to the first power. Let's do the next one. Next one's going to be minus. And what do you get there? Well, I factored out, oh, by the way, the 2's cancel off. The minus sign I've already taken care of. I factored out 2 pi x. And I factored out 16 minus x squared. So what are you left off with? You left off with an x squared. All right, make sure of that. I got to 2 pi x. Got the minus sign out. Yeah, I think I'm okay. All right, it looked pretty complicated. Let's write this down over here. So I'm going to write down 2 pi x. I'm going to put the root in the bottom now. That's 16 minus, whoops, that doesn't look right. 16 minus x squared is the root of that. And what goes on the top? It's going to be 32 minus 3x squared. All right? Now again, I want to go back and talk about, there's restrictions on the x gap between 0 and 4. So let's take a look at this over here. And I'm just analyzing, this is a derivative, by the way. So I want to do some analysis on that derivative, but I have to stick between 0 and 4. I'm kind of looking at that, and certainly 0 is not a critical number. You're not in the domain of this thing, and I'm going to say 4 is not a critical number because it's not in the domain of this thing. And the only thing I have to really look at is 32 equals 3x squared when it becomes 0. Divide both sides by 3. And x would equal plus or minus, by the way, the square root of 32/3. Now granted, looking at that, the 32/3, roughly 10 point something. I'll just put a number, it's certainly between 0 and 4, by the way. I know it's tough. I have to take a test point between 0 and the root of 32/3. I'm going to say 1. If you plug it in, you get positive. What does it mean? It means the volume function is increasing, right? Now, if I want to take a number after 32/3, and I'm thinking about a number after 32/3, and 32/3, it's roughly 10, right? So I guess the square root of 10, like 3. So it's got to be like, it's got to be above the 3 point something. So I'm going to play it safe and say 3.9. Because I know 3.9, if you square it, you get close to 16. But you plug it in, and when you plug it in, you're plugging it over here. All right, and if you did that, I hope you realize that you're getting something that's going to be negative. All right, now some of you that I need a calculator to do that. I'm not using a calculator, nor am I doing actual computation, I'm just thinking. Decreasing. So what did you just accomplish over there? I got a maximal volume now with that number. And I got to get over here and say, I wonder what they asked for, and find the largest possible volume. So I think I'm ready to do that. And what's that going to be? Well, I need the volume function. I need to evaluate the function at the root 32/3. I'll put this over here. Right, with that, I have to put that over here. So I have to put volume down of root 32/3. It looks painful. And this is the volume function over here. I'm going to write it down for you. Pi 32/3, the root of it, when you square it, becomes 32/3, times 2. Then you get the root. It's going to be 16 minus 32/3. Let's keep moving. I get 64 pi over 3. Let's see if we can do that root. Let's see, 3 times 16, and then minus, that's going to be what? 3 times 16, that's 30, and 18, 48. 48 minus 32 is 16. No, isn't that convenient? What do you have here? 64 pi. The square root of 16 is 4. And then what do you get on bottom? You get 3 root 3's. This is 256 pi over 3 root 3's. And again, they didn't give me any measure on this thing over here. So the volume is, I'll put this on the bottom, by the way. The volume, the question here, the volume, 256 pi over 3 root 3. By the way, I'm sorry to do that. I got to go back and look at that. 256 pi over 3 root 3's. I'm going to put a box over here. And they're cubic units, by the way. So that one's done. And let's see if we can get the next one going. Now the next one, yeah, looking at it, they have a picture. I'll just trust the picture, by the way. And I kind of like that because sometimes I'm reading something, I wonder, could you give me a picture of what I just read? And I see this over here. It says, you know, a rectangular package to be sent by the Postal Service can have a maximum combined combined length and girth. It's a perimeter cross-section. And by the way, the cross-section is a square, all right? So anyway, it says it's got to be 90 inches. So let's break this down. So the perimeter, the maximum it could be is 90. And what does that mean? Well, I got to do the cross-section's perimeter, which is 4x, and then the length of the object, which is going to be y. So this is a given. This has to be met, all right? And I can't exceed that. So a rectangular package to be sent by the Postal Service can have a maximum combined length and girth of 90. See the figure, I just did that. Find the dimensions of the package of maximum volume. Well, the volume of this package is going to be, let's see, x squared. That's the cross-sectional area, by the way, times y. But remember, you want a function of one unknown. So I can write it as a function of x. That's going to be x squared. And what's y going to be? Well, it's going to be 90 minus 4x. I'm going to simplify that. And that's going to be 90x squared minus 4x cubed. I'm going to keep moving through that, take its derivative. You can get 180 x. Oh, by the way, before I go on, x has got to be greater than 0. All right? 180x minus let's take a look at that. Oh, you know what? I could also bound x on the upper. Let me just do that for a second. I'm sorry about that. So the x greater than 0. And if I shrunk the y down to 0, what's the most x could be? It would be 90 over 4. And 90 over 4 would be equal to 22 and a half. All right, let me keep going over here. So you get 12x squared. I'm going to factor that. I'm going to pull a 12 out. I can pull an x out. 12 times 15. Let me just check that. 12 times 15, you're going to get, 10 times 15 is 150, and 2 times 15 is 30, so 180. And then minus x. Right, get some critical numbers here. They must fit between 0 and 22 and a half. All right, so certainly 15 is the only one. All right, 15. What am I going to do? Test it out now. And what do I test? Test the number below 15 and above 0, like 1. Plug it in, it's positive. Again, this is a derivative we're analyzing here. Above 15, like, I don't know, 20 or so, it's going to be negative. So I got the maximum here, and let's write this down. So they're measuring in inches, by the way. So it's going to be 15 inches. Is what x is. By 15 inches, that's what x is. By, and what's the length of that going to be? Well, I'm going to do this over here, and 4 times 15 is 60. 60 from 90 is 30, so it's going to be 30 inches. all right, 15 by 15 by 30. Let's go to the next one. And the next one's an open box, open top box that's constructed from a square piece of cardboard that's 6 feet wide. That means it's 6 by 6. Let me just make sure I read that correctly. A box with an open top is constructed from a square piece of cardboard 6 feet wide, so 6 feet. And what they do, they're cutting out the corners. I'm going to say they're cutting out little sections like this, XX, 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 XX. All right, so what's the volume going to be? Well, if you look at it, it's going to be square in the base, by the way. And what's going to be? It's going to be 6 minus 2x squared, right? And that, what we're doing is a dimension here. It's 6 minus 2x is going to be squared. We're just doing the base of it, this thing over here. What's the height of it going to be? X. All right? Okay. What am I going to do now? I guess I got to simplify that, don't I? So I'll write down V as a function of X. X times, I'm going to do 36 minus 24x plus 4x squared. I'm going to multiply that out, and I'm going to rearrange a little bit. 4x cubed minus 24x squared plus 36x. I'm going to take its derivative now. That's 12. Oh, by the way, before I go on, I want to point out x got to be greater than 0, and it has to be less than what number? 3, right? Couldn't exceed that. All right, so you get 12 x squared minus 48x plus 36. I'm going to factor that and get 12. And then what do you get? You get x squared minus 4x and plus 3. I'm going to factor that, and it's going to be x and x, 3 and 1. Now it looks like I'm getting minus minus. Let me just check that. Yeah, it works fine. All right, this is the derivative again. We're going to analyze the derivative on the number line between 0 and 3. I only have one critical number, which is 1. You can do a test point now between 0 and 1. And a good test point to choose would be like maybe a half. And if you plug it in, you're going to get a negative times a negative, which is positive. All right? If you take a number after 1, like, 2, what are you going to get? Positive times a negative, which is negative. So we got the maximum volume at this point. And what's that going to be? Let's write this down now. It's going to be the volume. I think that's what they're asking for, right? Find the largest volume. It's going to be the volume divided by 1. So it's going to be 6 minus 2. We're using this formula over here. Squared times 1, which is going to be 4 squared, which is 16, times 1, which is 16. So what's the answer over there? It's going to be 16 cubic feet. All right, that one's done. Let's go to the next one, which is number 8, which I think is the last question. And the last question is a box with a square base and an open top must have a volume. Well, let's put this down, put the box down. A box with a square base, x by x. I'll give it height of y. And put the box down over here like this. Again, your box doesn't have to be like really well drawn, but enough for you to understand what we got over here. So the volume is really just x squared times y, and they tell me the volume is 32,000. All right, find the dimension of the box that minimize the amount of material used. Well, the amount of material used, I'll put it down. This is going to be material. I'll call it M. Well, the base is x squared. That's the material from that. And then there's 4 sides, and those 4 sides have a dimension of x by y. Right, so I'm going to write material down as a function of x. That's going to be x squared plus 4x times y. And what's y? It's 32,000 divided by x squared. I need to simplify that and get x squared. I can write down 4 times 32,000. And then I'm going to say times x to the minus 1. All right. I guess I should talk about what x could be, by the way. X definitely has to be greater than 0. All right. So let's put this down now. Let's get the derivative over here. 2x minus 4 times 32,000. You may wonder why I'm not multiplying that. It's not important to multiply that because I'm not even at the stage of getting a number at this point. And that would be x to the minus 2. All right, so I'm looking at this thing and I realize that my critical numbers have to be above 0. So I want to look at this thing over here. I know that 0 is a critical number, but it's not because it's not in the domain of not in the domain of this problem over here because it can't be 0. So I'm looking really at 2x is equal to 4 times 32,000 over x squared. So I'm gonna put this down. And careful about it too. It's gonna be x cubed multiply both sides by x squared. I can divide both sides by 2, and I get 2 times 32, and I'm gonna say times 1,000. All right. Now I'm gonna just write that a little differently. X cubed equals 64 times 1,000. And what would x equal to? The cube root of that? Well, the cube root of 64 is going to be 4, because 4 times 4 times 4 is 64. So it's going to be 4. And the cube root of 1,000 is just 10. That's going to be 40. All right? Now, granted, you might say, I can't remember what the question is. Go back and read it. Oh, you know what? We have analyzed derivative. Sorry about that. Forgot all about that. Start at 0. 40 critical number. And we'll plug it in. Plug it right over here. Plug in 1, what would you get? Definitely negative. All right, let me just check that again. If I put 1 there, it's going to be 2 minus, yeah, it's going to be minus an enormous negative number. Now, if I go above 40, I don't know, like 1,000,000, it's going to be positive. All right, so it definitely minimizes the material function. So what was the question now? Oh, find the dimensions of the box that minimizes the amount of material to use. So these are in centimeters, so I know the x now is 40. So it's 40 by 40, 40 centimeter by 40 centimeter. That's the base, by the way. And what's the height of it by, well, let's be careful about this. I got to do some arithmetic now, right? So I'm looking at this, and I'll write this down again. So it's going to be 40 squared. I'll write down 40 times 40, by the way, times y. And I'm going to say 32 times 1,000. All right, I'm going to divide both sides by 100. You can get 4 times 4, y. And you get 32 times 10. All right, what I'm going to do now, I guess divide both sides by 16. And what do you get? 2 times 10. What's 2 times 10? 20. That's my answer. Numbers seem to work out pretty nicely, by the way. So again, the dimensions, 40 by 40 by 20. All right, these are in centimeters. Let me see if there's another question. And there's not. All right, we're done with that. This is an optimization worksheet. Could be an optimization exam as well, by the way. Thank you.